Okay, hello everyone, welcome back to another updating part of the RTOS real-time operating system. As I said in previous part, in this part I want to implement SemaphoreRelease from interrupt and SemaphoreGet from interrupt. Okay, in previous part I said there are some problem when you want to request a system call from interrupt. Okay, but in this part I want to implement SemaphoreRelease and SemaphoreGet and resolve these problems. But if you go to the repository of the project, Untitled project, in commit number 17, I've updated the project under this commit, initial addition of system call from interrupt. Okay, and from this commit, the RTOS supports system call from interrupt, but in this commit I just implement SemaphoreGet and SemaphoreRelease from interrupt. Okay, but let's back to the slides. So in this part I want to talk about SemaphoreRelease from interrupt and SemaphoreGet from interrupt. But as I said in the last slide of previous part, I said when you want to send your argument to the kernel, you must send system call arguments to the kernel by using of this array. Okay, by using of this array. If you go to the RTOS include and RTOS type definitions, here in kernel control block you can find this array, interrupt request array. Okay, and by using of this array you can send your arguments from interrupt to the kernel. Okay, but let's just see the structure of interrupt request array. When you have a system call from interrupt, okay, system call from interrupt, and you want to send arguments and system call number. Okay, you know you need to send system call number to the kernel by using a global structure. When you want to send argument and system call number from system call that's called from interrupt to the kernel, you must put a specific and global structure. A specific structure is collection of arguments, and global structure created from two parts: system call number and a pointer to a specific structure. Okay, you must put a specific and global structure elements to this array, Okay, but let's see the structure of this array. Okay, this is the array created from some elements. Okay, and the width of array is a word, is 4 bytes. Okay, is 4 byte 0, 1, 2, 3. Okay, the width of each element is a word. Okay, and when you want to change the number of elements, you can change this value: interrupt request element count, and this defined here, element count, okay, equal to 8. Okay, so this array created by some elements, but let's to see the structure of each element. Each element created from some words. Okay, for example, at this time 8 words. 1 0 1 2 3 4 5 6 7 8. Okay, the size of each element is at this time is 8 word, 32 bits or 4 bytes. Okay, the array created from some element, each element created from these words. Okay, this is the structure of for example, this is element 0. Okay, element 0, and you have at this configuration you have 8 elements. Okay, and this is the length of each element. Okay, length of each element is 8. You can say length of each element is 8 words. You can change the value of element length from this part. Okay, and size of array, and the total length of array is length, element length multiplied by element count. Okay, for example, at this time 8 word multiplied by 8 is 64 word or 256 bytes. Okay, you must use this data structure, this array, to send your arguments and system call number and other things to the kernel. But how you can send arguments and other things? Okay, let's inspect this structure, each element. First word of each element called like word. And when you want to send your arguments to the kernel, you must acquire, and system call must acquires one of these elements. And when the RTOS allocates one element to one system call from interrupt, change the value of lock to the 1. Okay, 1 in this word means this element has been locked by one system call. Okay, after that, 2 next words is global structure. You know, global struct created from 2 words. You can see here in this header file, RTOS type definitions.h. Okay, you know, global struct or kernel system call arg structure created from 2 words. First is system call number, and after that a pointer to a specific structure, a structure of arguments. Okay, so you need to send these 2 information and data to kernel. When you want to send this data to the kernel, you must put these values in word 1 and word 2. Okay, and when you want to send arguments of a system call to the kernel space system call, you must put your arguments in other words. Okay, for example, at this configuration, the maximum arguments, the maximum number of arguments is 5, but you can change this, the maximum number of arguments, by changing the length. Okay, by changing the length. So we can use interrupt request array to send system call number and a pointer to a specific system call and arguments to the kernel. Okay, system call number. You need to send system call number to the kernel system call handler. You need to send pointer to a specific structure to the kernel, and you need to send a specific structure to the kernel, a structure of arguments. Okay, but let's describe system call from interrupt and describe using of interrupt request array by implementing SemaphoreRelease. Now I want to implement SemaphoreRelease from interrupt. Okay, and I want to use this data structure to send some information to the kernel from an interrupt. Okay, but before to start the implementation of the SemaphoreRelease from interrupt and SemaphoreGet from interrupt, you must know and you should know, in new implementation of Semaphore there is a little difference in implementation. But what's this difference? When SemaphoreGet is called, if the value of semaphore count was 0, semaphore count was 0, RTOS will decrease semaphore count to the negative numbers. In previous implementation of Semaphore, when the count was 0, the operating system doesn't decrease this value anymore. Okay, but in this implementation, when the value of semaphore count is 0 and you have calling SemaphoreGet from thread, the operating system change the value of semaphore count to -1. If another time call SemaphoreGet from thread, another time decrease the value to -2. Okay, and this value and the negative value shows the number of weighted thread. When the count is 0 and you call SemaphoreGet from thread, the RTOS decrease the value of count to -1. This means 1 thread weighted. Another time, if you call SemaphoreGet from thread, decrease the value to -2. This 2 means 2 thread weighted for semaphore. This is an initiative way, and by this way you can easily implement SemaphoreRelease and SemaphoreGet from interrupt. Okay, this initiative way, decreasing the semaphore count to the negative numbers, make the implementation of semaphore from interrupt, SemaphoreGet and release from interrupt easier. Okay, but this is the new implementation of SemaphoreRelease. SemaphoreRelease from thread, okay, not from interrupt. When the value of count is greater than 0 or equal to 0, just do count ++ to release the semaphore. But when the value of semaphore count is a minus number, is a negative number, this means some thread waited for semaphore. You must do count ++ and return most prior thread. Okay, but at this time, to support system call and SemaphoreRelease from interrupt, you must change the value of semaphore count by using of atomic function in atomic part. Why? Because when RTOS wants to change this value in kernel space, okay, you know you can change the value of semaphore count in kernel space system call. Okay, there may be an interrupt that wants to change the value of semaphore count, because at this time semaphore supports system call from interrupt. Interrupt can change the value of semaphore count, and semaphore count shared between interrupt and kernel. Okay, and to prevent conflict between kernel and interrupt when using this share value, you must change the count of semaphore count by using of atomic function in atomic parts. Okay, but let's inspect the code, and inspect the code is better. Open semaphore. Here is SemaphoreGet. Sorry. Here is SemaphoreRelease. But at this moment, at this implementation, if you want call SemaphoreRelease from interrupt, you will not have an error in return value. Okay? But like before, if you call this system call from thread, operating system put the value of arguments in a specific structure and other information in a global structure and call kernel system call. And in this function, jump to SVC and run kernel space system call, but change the value of semaphore count in atomic part by using of atomic read and atomic write. First, atomically read the value of semaphore count. If the value is greater than or equal to 0, just increase the value of semaphore count. But if the value of semaphore count is maximum count, at this part, return error. Okay? So, greater than 0 or equal to 0, count plus plus. But if the value of count is smaller than 0, is a negative number. If greater than 0, do this part. But if smaller than 0, do count plus plus and return most prior thread like before. But you must change the value of semaphore count by using of atomic functions. Okay? This is SemaphoreRelease from thread. But as I said, in this part I want to talk about SemaphoreRelease from interrupt. Now let's inspect SemaphoreRelease from interrupt like before. If the count is greater than 0 or equal to 0, just count plus plus. This value means no thread waited for semaphore. Another time, SemaphoreRelease system call, user space system call. If called from interrupt, call this function SemaphoreRelease from interrupt. This function is a static function. Okay? Another time, in an atomic part, the value of semaphore count shared between interrupt and kernel space. Okay? So Another time, if the value of semaphore count is greater than 0 or equal to 0, semaphore count plus plus and return OK. Okay, return OK. But otherwise, if the count is smaller than 0, if the count is a negative number, do count plus plus, but request return most prior thread. Okay, request from interrupt. This is a request from interrupt, and when you want to request from interrupt, you must use interrupt request array. Okay, but before talking about request from array, let's talk about another thing in this implementation. Here, when you call SemaphoreRelease from interrupt, you must return value. You must have return value at this point. Okay, at this point, this function must acquire the value of return value. But when you call a system call from thread, you can acquire the value of return value in kernel space system call, for example here. Okay, for example here. But when you have SemaphoreRelease from interrupt, this function can acquire the value of return value at this time. At this time, if the value of count equal to maximum, the return value is error. Otherwise, the return value is okay. Here in this function, another time, SemaphoreRelease from interrupt. Here, if the value of semaphore count is equal to max, the return value is error. Otherwise, return value is okay. Okay, you must acquire the value of return value at this point, because first you return from this function, after that jump to kernel space. You can't acquire this value from kernel space, because first you return from this function. When you call SemaphoreRelease from interrupt, the interrupt priority is greater than SVC priority, and first return from this function, and you must acquire the value of return value according to the count number, according to the semaphore count. Okay, but when you call SemaphoreRelease from thread, first jump to kernel, run this function. After running this function, another time return from kernel space to thread space and acquire the return value at this point. Okay, this is the difference between system call from thread and system call from interrupt. Before to jump into the kernel, you must acquire the value of return value. Okay, in your system call. But let's talk about request return most prior thread. Another time, let's inspect this function. When you have SemaphoreRelease from interrupt, the operating system run this function. In this function, if the count is smaller than 0, is a negative value. If the count is greater than 0 or equal to 0, do this work. But if smaller than 0, do this part. Do semaphore count plus plus, write atomic this value to the semaphore count, and if the write is successful, run this function kernel interrupt request alloc. Interrupt request alloc. What's this function? What's this function? But this slide related to return value. I talked about return value. Okay. I said according to the value of semaphore count, you can acquire the value of return value. Okay, before returning from system call from interrupt. But to use interrupt request array, you must call kernel interrupt request alloc, this function. This function defined here. Kernel.h here. Okay, let's just see the implementation of this function in kernel.c. Here is the implementation of this function. But what does this function do until here? Okay, what does this function do? You must call this function to acquire an element from array. Okay, allocate an element from array. Allocate an element from this array. Okay, allocate an element and change the value of lock from 0 to the 1. Okay, so this function, according to the interrupt request element count, allocate an element. Okay, and when you call this function return this value, address of this word. Okay, this pointer, a pointer to this part of element, second word. Okay, a pointer to the second word. This function return pointer to the second word of element. Okay, so you have a pointer to this word in this element. So this is the return value of this function is pointer to second word of element. So you can put the value of system call number. This is a system call number, but at this time SemaphoreRelease from interrupt system call number. Okay, it's an kernel space system call from interrupt for SemaphoreRelease. You can put the value of system call number in this address, memory point or pointer plus 0, pointer plus 0, plus 0, plus 1, plus 2, plus 3, 4, 5, and 6. Put the system call number at this word. Put the system call number at memory plus 0. Put the ID, semaphore ID, to pointer plus 2, to pointer plus 2 first argument, semaphore ID. At this time, semaphore ID. Okay, and put the address of memory plus 2. Memory, what's the memory plus 2? Is here. Memory plus 2 here is here. Address of specific structure. Okay, memory plus 2 in memory plus 1. Put pointer to a specific structure, this address. Instead of putting the arguments and data in global struct and a specific struct, these local variables, you must put the arguments, system call number, and pointer in this element and send the address of global structure to the kernel. When you want to have a kernel system call, you must send a pointer to global structure to the kernel. You must send this pointer. Okay, you must send this pointer to the kernel. Okay, in a regular system call, you must put the address of global structure to the system call here, but when you have a system call from interrupt, you must send this pointer to the kernel. Now in kernel, you can acquire the value of system call number, pointer to a specific structure, and in a specific structure your arguments. In a semaphore release, you need to send semaphore ID to the kernel. And according to the semaphore ID, kernel check semaphore waitlist and return most prior thread. So at this time, send argument to the kernel by using of interrupt request array. Another time, when you have semaphore release from interrupt, call this function semaphore release from interrupt. Okay, and in this function, according to the value of semaphore count, acquire the value of return value. But if the value of semaphore count is smaller than 0, do semaphore count plus plus and send the argument to the kernel by using of kernel interrupt request array. Okay, and what is the request? Return most prior thread. I said here is number of kernel space system call semaphore release from interrupt system call number, and here is a new kernel space system call for semaphore release from interrupt, semaphore release from interrupt system call. Okay, and like before, in argument you have the address of a specific structure. Okay, a specific data structure, and by using a specific data structure you can acquire the value of semaphore ID. And another time you must acquire and calculate this value pointer from this value. Address of this pointer, for example, pointer plus -2 equal to the address of this pointer. Another time you must acquire the value of this pointer, argument -2, argument address of a specific structure here, -2, it's this pointer, and put this value in this function kernel interrupt request free. Okay, and by using of this function you can return the element to the kernel and unlock the elements. Okay, you can return this element to the kernel and unlock that by writing 0 to the lock value. Okay, And in this system call, kernel space system call, you just need to return most prior thread. Acquire the most prior thread, list get max semaphore wait list, delete most prior thread from wait list here, and insert it to ready list like before. Okay, so in SemaphoreRelease from interrupt, if the value of count is greater than 0 or equal to 0, just do count plus plus. But if the value is smaller than 0, do count plus plus, but you need to return most prior thread. You need to send this request by using of interrupt request array instead of global and specific structure as a local variable. Okay, but the implementation of SemaphoreGet is simpler than SemaphoreRelease. If the value of count is greater than 0, do count minus minus, but if the value of count is 0 or smaller than 0, according to the timeout, if the timeout is 0, like before, return error, and if the timeout is greater than 0, put the thread to the wait list. But when you call SemaphoreGet from interrupt, just if the count is greater than 0, do count minus minus, but if the count is equal to 0 or smaller than 0, return error, because in calling the system call from interrupt, there is no thread to put to the wait list. Okay, here is implementation of SemaphoreGet. Like before, if it's not called from interrupt, do these works like before. Put the argument in the specific structure and global structure and call kernel system call. But if the system call called from kernel, called from interrupt, run this function SemaphoreGet from interrupt. In kernel space system called from thread, regular kernel space system call, like before, because semaphore count is shared between interrupt and kernel, you must change the value of semaphore count by using of atomic functions. If the value is greater than 0, when you call from thread, just decrease the value. But if the value is 0 or smaller than 0, if the timeout is 0, return an error. Otherwise, semaphore count minus minus and put the thread to the wait list. Delete from ready list and put thread to the wait list like before. But if called from interrupt, run this function. Run this function. Another time a static function. Another time you want to change the value of semaphore count. You must change this value by using of atomic functions. If the count is greater than 0, return OK. But if the count is smaller than 0 or 0, return error. Okay? And use this return value here. Okay? And this function acquires the value of return value, not kernel, when you call from interrupt. Okay, but let's see an example here. In this example, I've used external interrupt. If you see if you see my board here, this blue button, this blue push button, for this blue push button I've activated an external interrupt. Okay, for the this push button I've activated an external interrupt, and when you push this button on board you will have an interrupt, and in this interrupt I want to release the semaphore. Okay, and I've configured my board here and config external interrupt. Okay, if you want to know how you can activate an external interrupt in STM32 microcontrollers, you can refer to the documentation of STM32. Okay, and it's out of our topics, but I've activated an interrupt, an external interrupt on my board, and when I push the push button, the processor jump to this function, to this handler, and run this function, SemaphoreRelease, but at this time from interrupt. But here is my example. I have two threads, thread 1 that has priority high and thread 2 that has priority normal. I have a semaphore. The initial value of semaphore is 0. Okay, in thread function 1 with priority high, first I get the semaphore, but because the initial value is 0, the operating system will put the thread to the wait list for 500 milliseconds. But before elapsing this delay, if I push the button and run this handler, this function release the semaphore, and this value status will be OK, and I can toggle the LED on my board, green LED on my board. But if this function return with an error in return value, after elapsing this delay time, the waitlist handler will return the thread to the ready list, but the status is error. At this time, processor does not run this if block. Okay, so if I push the push button, the processor jump here and do semaphore release. Okay, and by releasing the semaphore, the processor immediately run thread function 2. Okay, because it has higher priority, and the status value will be OK, and toggle the LED. So let's debug the project and see the result. Okay, here is my example, and let's put a breakpoint here. Okay, and run the code. Now if I push the button, the processor will jump to this handler. Let's push the button. 3, 2, 1, and push. Okay, now the pointer point to this line. Okay, because of interrupt. Now let's run SemaphoreRelease from interrupt, because SemaphoreRelease call from interrupt, operating system jump to this line. Let's go into this function. Now get the semaphore value. You can see the semaphore count is -1. This means one thread waited for this semaphore. Now I want to release the semaphore. Get the semaphore count. Semaphore count is -1. but because semaphore count is a negative value, jump to the else block, to semaphore count plus plus, and write the value to the semaphore count. And if write is successful, request, send a request to the kernel by using of interrupt request array. Okay, write the value in element and call kernel system call, but at this time put the argument in kernel system call list. If the write is successful like before break, and call kernel system call request. But I said in previous part, when you want to call kernel system call from interrupt, you must first set pendSV, and in pendSV handler you must request for SVC. In this function you can see first set system call request in kernel control block, but if you are in interrupt, run this function. What's this function? Set pendSV, not SVC. Return from this function, doesn't jump to pendSV because pendSV has lower priority than interrupt. And return to this function and return to this function, SemaphoreRelease from interrupt. And now return value is the status OK. Return value is the status OK, and return from this function. Now return value is status OK. Release from user space system call, but doesn't jump to kernel space because interrupt has higher priority than kernel. Return from this interrupt, and after that jump to pendSV handler. And at this time check if you have a system call request by using of this label, by using of this part of code. Now set SVC. Okay, so when you want to call a system call from interrupt, you must first call pendSV, and in pendSV at this line call SVC because interrupt has higher priority than SVC, and you can't call SVC from a higher priority, from an interrupt that has higher priority than SVC. Okay, but if I run my code will return to thread function 1 because at this time I released the semaphore. Now code is here and status is OK. So let's do another time run this function. Okay. Sorry. Let's delete this breakpoint. Another time put this breakpoint, reset, run the code, and press push button. Now I'm here. Okay. Now another time if I run my code, the code will return here and the status value is OK. Okay, thread function 1 return to the ready list by using of SemaphoreRelease from interrupt. And because status is okay, because the value of the status is okay, you can toggle the LED. Because this value is too short, I can't acquire the status at this port. But let's stop the project and run code here in the webcam and see the result to you. Here is my board. Reset by black button and push blue button. Okay, by pushing this blue button I can toggle the LED. Okay, here is the result on my board. Another time you can release a semaphore from interrupt, and in this way you can immediately return a thread to ready list by an interrupt. In previous part I said, assume in your car you have a computer, you have a microcontroller, and in this microcontroller you have a thread to control the ABS brake. When you push the brake, you want to immediately run a thread. Assume here the push button on my board is an ABS brake, is a brake. When you push this button, the operating system immediately return to this function, and the status value is okay, and toggle the LED. Okay, so here was an implementation of system call from interrupt. But before to finishing this part, let's see this slide. To implement SemaphoreRelease from interrupt, we need to change the content of waitlist handler in kernel.c. Why do we need to change this function? Let's see first this function here in kernel.c. Here is waitlist handler. You must change the content of this function. But as you can see, if the current thread equal to return tick like before, you must return the thread to the ready list from waitlist because the delay has elapsed. But if the thread waited for semaphore, you must increase the value of semaphore count. You must increase the value of semaphore count because I said here a negative value shows the number of waited thread. When you want a waited thread from waitlist to ready list, you must increase the value of semaphore count because the value of semaphore count shows the number of waited thread. Here you must, if thread waited for a semaphore, you must increase the value of semaphore count here by using of atomic operations, because semaphore count shared between kernel and interrupt. But if thread waited for mutex like before, delete from waitlist and insert it to ready list. Or if thread is not waited for a resource, just delete from wait list and return it to ready list like before. But if waited for a semaphore, you must increase the value of semaphore counts. Okay, but this part was a difficult part. I know it's a difficult part, but you can see this part more than one time to find out completely the structure of system call from interrupt. Okay, now by using of this data structure interrupt request array, you can send your request from interrupt to the kernel. Okay, and you can support system call from interrupt. You can implement system call from interrupts for other system calls. For example, thread resume. You can implement thread resume from interrupt. I think in next part I will implement thread resume from interrupt. That will be a good option and good facility in the RTOS. But for example, you can't implement SemaphoreGet or SemaphoreRelease from interrupt because SemaphoreGet related to a thread and SemaphoreGet needs an owner, and an interrupt can't be an owner. A thread can be an owner. Okay, because of this reason, logically you can't implement SemaphoreGet or SemaphoreRelease from interrupt, but you can implement other system calls from interrupt. For example, set priority or other system calls. And for example, you can't implement thread wait from interrupt because by using a thread wait, you want to wait and make a delay for a thread, not an interrupt. Some system call logically can have system call from interrupt, like SemaphoreRelease and SemaphoreGet, but some other can't, like SemaphoreRelease, SemaphoreGet, and thread wait. But I think, as I said, in next part I will implement SemaphoreRelease from interrupt. That will be a good practice. Thank you. So very good. These two parts were updating parts, and in these two parts I've implemented system call from interrupt and SemaphoreRelease from interrupt and SemaphoreGet from interrupt. And another time you can see by using of this push button you can call a system call from interrupt. Very good. So very good. Thank you very much to see me, and see you soon in the next updating part. Thank you very much.